Mattias is currently a quantum computing researcher at Ringer Ingelheim. He has a background in he has a background in quantum chemistry and has done quantum many body problems from both the classical and quantum computing field. Before he received a PhD in physics from Ghent University on Green's function, and has done postdoctoral research at Kent University, Rice University, Harvard University, and at University of Toronto. And today he's going to be talking about his recent work, which deals with simulating large-scale protein-ligand interactions on a near-term quantum computers. So Mattias, without any further ado, please go ahead.
All right. Thank you for the intro, Abhinav, and it's great to see you again and to be on this seminar series. So as Abhinav said, I'll be talking about recent work that we did with QCware, which is a company out of California. And it's the team of Rob Parrish and Fionn Malone who did a lot of the work. And it's a very happy instance because it's our first paper as the quantum lab at Boehringer, and we made it to the cover of Chemical Science. So we were really happy of that, about that. So the thing we tried to calculate in this project is the binding free energy. And for those who don't know what that is basically the energy that you gain by bringing a molecule closer to another molecule. And in this problem, we mostly think about bringing a drug close to a protein such that you can inhibit or activate its function. So it happens a lot in the context of drug design. And normally you would look at the binding free energy, so the Gibbs free energy, where you include volume effects and also entropic effects, so changes in conformations when you approach or remove the two molecules. But yeah, in this project, we've looked only at the static things, the static interaction energy, where there's no geometric relaxation, and just for simplicity's sake and to make it tractable. So why is this important? So we calculate this binding free energy in two cases. So one is in the hit to lead phase of the drug design process. That is where you compare different types of molecules among each other, and you check which one has the best function. And then also in the lead optimization phase, where you have your lead, so you know which type of molecule you want to use as a drug, but then you make tiny changes with respect to ligands or functional groups, so that you either increase the potency or you decrease the toxicity and side effects, so or side functions, where it also inhibits another protein, for instance. So it's a very important quantity that determines a lot of the properties of your drug. And we want to improve this, so we can currently get measurements from the lab. So we can send this molecule off to the lab, they synthesize it, they do measurements in a calorimeter, and they tell us what the binding free energy is, but that takes a lot of time and costs a lot of money as well. And there's also more technical reasons, and that is that some of these proteins have metal centers in them, and they are really hard to treat with classical computation, and that's why we want to look at quantum computing here. So what is the current approach? So currently people are mostly brute forcing this. So you calculate the energy of the two molecules together, you subtract the separate energies of the monomers, and that gives you the interaction energy. So there's two problems with that. So you have a lot more degrees of freedom when you bring the two monomers together. So you have the basis superposition error, and that forces you to also do larger calculation for system A and B separately. So it's an increasing cost. And on the other side, you also have a subtractive procedure where system A and B together have an enormous energy. And then you are looking for this tiny difference when you separate them. And this, like you see the orders of magnitude here, and this just requires a enormous relative accuracy to calculate these energies, and that's really hard. So we take another approach, and that's this additive approach that energy decomposition methods offer. And you can see the formula here. It's just a reordering of what we have before, but it really captures what we want to do well. So instead of calculating this difference, you now say that the system together consists of system A, B, and then whatever happens between them, so the interaction energy. And now instead of going to calculate A and B together, you now build up the interaction energy out of terms you are interested in. And that's exactly what happens in these energy decomposition methods. And if you're interested in that, there's a paper by our computational group that explores all kinds of these methods. And we will focus on one specific one, and that's the Symmetry Adapted Perturbation Theory. And what's special about that is that instead of doing the decomposition on the energy level, you do it on the Hamiltonian level. So you do you split the Hamiltonian in terms that act on energy electrons on the monomer A and monomer B, and then you are left over with a tiny part of interaction Hamiltonian, and that's what's in this V tilde. And you can clearly see, so the electrons on monomer A and B interact through Coulomb, and then the attraction to the nuclei for the electrons on B to the nuclei on A, and reverse for the electrons on on A to the nuclei of B, and then the nuclei of A and B also repulse. So, and then you take this tiny interaction and you do what you always do. Then you do perturbation theory in this, and you start decomposing the energy in first order, second order, third order. And what's special about the SAPT is that at each order, you also restore fermionic antisymmetry. So if you take system A and system B and you treat them together, you put their wave functions together as a product wave function, but this means that there's no exchange symmetry between the electrons in system A and B, and you treat them as distinguishable, but they are not, so you need to correct for this. So this has plenty of advantages. So it's additive, so the cancellation, like this giant relative precision is not necessary. You have a perturbation order, so if you think that your contribution is still too large, you can go one order of perturbation theory beyond this. And then there's also a nice physical interpretation of what you get. So you see below the decomposition of the energy in the orders. So you have the first order polarization. So this is the first contribution, and then you all directly have an exchange equivalent of that, and then the second order, and then an exchange equivalent of that as well. And the first order polarization, that is exactly the electrostatics of this problem. So it's the charge on system A interacting with the charge on system B. And then the second order polarization is are two dynamical effects. So you have the dipole induced dipole, so that's the dispersion, and then induction, which are just the the fluctuations. So these are fluctuations of the vacuum that then induce other fluctuations on the other system. In our current work, or in this paper, we've looked only at the first order, so the electrostatics and the exchange energy at first order. And that is mostly because the second order involves a full resolution of the identity. So you need to sum over all states in your Fock space, and that just takes like a heavy computation, and you need to approximate really intelligently, and that is left for a second paper that's forthcoming. So this is a depiction of the different terms. So the first one is this charge-charge interaction, and then exchange is a truly quantum effect. So you try to enforce the Pauli principle. Then you have the dipole-induced dipole, and the dispersion, which is the fluctuation term. So the dispersion is actually a truly quantum effect that you cannot have in classical methods. So now we have this previously in first quantization. Of course, you cannot compute well in first quantization. We try to digitize this, and we do this by introducing a basis set. So if you write, for instance, the first order polarization, you go from this tensor product of the wave functions, and you put the interaction operator in between it. So that's, I mean, the first order contribution to the energy is always just the expectation value of your potential. And what you get is a product of gamma and V bar. And here it's good to notice that all P indices are on system A and all Q indices are on system B. So what you remark instantly is that you only have PP and QQ on your density matrix on gamma, which means you don't need, you only need to calculate quantities on one of the monomers, or well, on both monomers, but only on one at the same time. So if you see below, the density matrix is an expectation value between the wave functions of A. So you can build this interaction term purely out of terms that need only the wave function of one of the monomers. For example, I've put the first order exchange term here as well, and I didn't expand it. It's more complicated. You need to, I think you have 5 terms, and it also turns out that the expression in terms of matrix elements is harder. You now, instead of only having the single particle density matrix, you also need the 2 particle density matrix. I mean, that's sort of expected since your interaction is 2-body. And you also need the interaction elements, of course. So you need the expectation values, the integrals of your Hamiltonian. And these are slightly changed compared to a regular second quantized Hamiltonian. And you now have these terms that come from the expansion of this interaction Hamiltonian in the 4, like the electron-electron Coulomb, the nuclei of A attracting the electrons on B, and so on. So it's really a nice expansion that makes perfect logical sense. So it's really nice to see these terms that appear. So what we now need is these matrix elements. So we get them from our classical calculation, our Hartree-Fock calculation. And we also need the density matrices. And for these density matrices, we'll use the quantum computer. So we'll use the variational quantum eigensolver. That's a very commonly used approach in NISQ that was developed in the Aspuru Gudzik lab. So you can read all about it in the review that we've written about quantum chemistry on quantum computers, and the link is below. And it comes down to the ages-old Rayleigh-Ritz principle. You propose the shape of a wave function, and in this case, the wave function ansatz will be the variational circuit, and then you optimize the energy, you minimize the energy over all of its parameters. And once you have the optimal parameters, you have the wave function, and you can start calculating expectation values with respect to it. And those expectation values will be the two-particle density matrix. So there's several limitations that make it the near-term and noisy quantum computing. So the coherence times are low. So this means that you can only do very short circuits or very simple wave function ansatzes. And this might not be a problem in our case, because we expect, like I said before, that this interaction energy is built constructively, so additively, and we expect that we don't need a very high accuracy on the density matrices, so we can get away with very sloppy wave functions, we assume. And then, of course, the second shortcoming of current quantum computers is that you have very few qubits that you can do something useful with, and this means that only very small systems will be treated, and that's a bit of a problem in pharma, and that really makes that the things we show are model systems. I mean, I don't think anybody currently can say they do real life applications. It's all models of what we plan to calculate once we can do more and quantum computers are more powerful. So now some words about the ansatz we will use, because it's a fairly new one. So what we'll use is a modified version of the k-layer unitary cluster Jastrow ansatz. So k-layer means that you repeat the same circuit k times, and the unitary means, yeah, it's a unitary ansatz. And the cluster Jastrow is a method developed by a Japanese group. You can see that's the first link on the slide, where they take a cluster ansatz that consists of density-density interactions, and they put amplitudes in front of it, and they use this as a sort of coupled cluster. We take another approach, and instead of having density-density, we have a pairwise excitation, but only between neighboring levels. So you can only jump from level 0 to level 1, and from level 1 to level 2, and so on, of course. There's some, the k between each of the large k between each of the k layers is a fermionic rotation. So it means that you change bases, fermionic bases, basically. And by changing fermionic bases between each layer, you give the interaction, the excitation operator more power, and you get a more expressive ansatz. There's some nice desirable features about this ansatz, and that's that it's number symmetry preserving. It's number symmetry preserving not only on the full number operator, but also on the separate alpha and beta number operators. And there's some work by QCware and Covestro that talks about this these Givens fabrics, and it's really easily decomposed in elementary Givens rotations, and really fits well in this framework that they've developed. So if we then go on and look at this full workflow, so what we'll do is we'll take a protein, find the active site and active space for this calculation, get matrix elements, put them into VQE ansatz, where below you see the one layer of the circuit that we'll use, and then we'll get density matrices, the single particle and two particle density matrix, and we'll put this into classical processing. So the classical processing is multiplying these density matrix with their respective interaction elements and adding it all. And the final goal is to rank drug molecules according to their potency. So that's what we're eventually trying to do here. So to first show the feature I told you about that we expect to get away with sloppy wave functions, you can see that happen here. So this is a test system where we approach p-benzene perpendicularly to a regular benzene, and we only treat the p-benzene as a quantum with the VQE ansatz, and we take RHF for the benzene. And on the left plot, you can see in blue the energy of the p-benzene in our VQE, and on the x-axis you have the number of layers. And you see that even for 5 layers, you're not approaching chemical accuracy, which would, or you're approaching chemical accuracy but not reaching it by. And with chemical accuracy, we understand the 1 kcal error line. And if you then look at the 2 terms that we have in SAPT, which is the electrostatics and the exchange, you see that even at k equals 1, you're 1 or 2 orders of magnitude below this chemical accuracy. And you're also seeing that it doesn't change too much with the number of layers. So if we then look at these terms separately, so that's the second and the third plot, you see that this behavior also persists along the whole reaction coordinate. So here we see the terms when you elongate this distance between the benzene and p-benzene. And okay, there is some improvement by going from 1 layers to 5 layers, but it's both are adequate already, and the electrostatics are more benefiting from more layers than the exchange. So then off to our model system. So we'll be treating a model of the KDM5A molecule, and this molecule is important for breast cancer, for instance. And here you can see that there's a heavy classical quantum chemistry involved to get this from these thousands of electrons, well, 1,400 electrons and 2,000 orbitals into the final form, which is 8 electrons and 8 orbitals. So to be able to calculate this on a quantum computer, you really need to throw away a lot of the details of what is happening and only keep the essential description of the problem. And that also has as a consequence that it doesn't really fully match reality, of course. So what you can see here is a plot of the experimental binding free energy difference, so on the x-axis. So that's from a paper for these 5 molecules you see on the left. They have, I think, experimentally determined the differences in binding free energy, and they find that compound 5 has the lowest binding free energy, then compound 4, then 8, then 9, and then 12. And so if we describe this well, then we would see that we get a straight line, and we get the same, well, a straight monotonically increasing line would mean that the order is also predicted by our computational methods, which are on where the interaction energy difference is on the y-axis. So
Mattias, it might be time to start wrapping up a bit. We're reaching the end of our.
So this is the last example. So almost done. So okay. As you can see, it is not a monotonically increasing line. So this means that we're doing something wrong. And so when we check this, so on the bottom you see our SAPT VQE, and although it is reproducing kcal very well, it is not predicting the right order. And then we went to investigate why that is. And on the top you can see that when you do RHF, it also predicts this number 4 to be lower. And once you do SAPT on RHF and you do the second order SAPT, this behavior is cured. So what this means is that we essentially need the second order polarization and exchange. But it was really nice to see that this VQE behaves as well as kcal, and you can indeed get numbers out of this that make sense. So the conclusions are that this is a really promising approach, because the necessary circuit depth to get a number that is meaningful is greatly reduced. So while if you want to calculate ground state energies, you would need 5 layers, we now only need 1 layer. The bad, of course, is that there's a lot of classical pre-processing needed, and to fit everything on a current quantum computer, it's really limiting the effects you can see. And then the ugly is, of course, that measuring density matrices on quantum computers is not exactly considered feasible. So this goes with the 2 RDM goes with n to the 4th power, so n being the number of orbitals. So this goes up really fast if your system grows, and it's probably not feasible for realistic systems. Yeah, so we like this example a lot, and we think it's a great target to one day execute on real hardware. And like I said, we're working hard to get the 2 additional terms out, and you'll be hearing from that hopefully soon. So
awesome.
Thank you for your attention.
Thank you very much. It's great to hear from you. Are there any questions for him? We have time, I think, for 1 question.
Okay. Am I reading to myself, or are you?
Jerome, you can just unmute yourself and ask.
Okay, thanks. Hello, Mattias. My question was, do you think the second order terms in SAPT will also be as noise resilient as the first order ones?
So the problem there is the sum overall states. So